Download this code from codegive.com, link in the description below. OK, let's dive into the fascinating world of bottleneck spanning trees. This is a specialized type of spanning tree with applications in network design, resource allocation, and more. We'll cover the concept, the algorithms to find them, and a Python code example. What is a spanning tree? First, let's refresh what a spanning tree is. Given a connected, undirected graph, a spanning tree is a subgraph that 1. Connects all vertices *, it includes all the vertices of the original graph. 2. Is a tree *, it is acyclic, contains no cycles. A graph can have multiple spanning trees. What is a bottleneck spanning tree? A bottleneck spanning tree, BST, is a spanning tree where the maximum edge weight in the tree is minimized. In other words, it's the spanning tree with the smallest largest edge weight. Why are bottleneck spanning trees useful? Imagine you need to build a network connecting a set of cities. The edges represent potential communication links, and the weights represent the cost, or latency, or bandwidth requirement, of establishing that link. A bottleneck spanning tree might be desirable if minimizing the weakest link * you want to ensure that the worst performing, highest cost, link in your network is as good as possible. This is particularly relevant if performance is bottlenecked by a single connection. Capacity planning * if the edges represent the capacity of a pipeline, a bottleneck spanning tree ensures the highest possible capacity is available throughout the whole network. Robustness * a bottleneck spanning tree can sometimes be more resilient to failures than a minimum spanning tree if it has less of a dependency on the most critical edge, s. Relationship to minimum spanning trees, MSTs. Interestingly, every minimum spanning tree, MST, is also a bottleneck spanning tree, but the reverse is not necessarily true. An MST minimizes the sum of the edge weights, whereas a BST minimizes the maximum edge weight. Algorithms for finding bottleneck spanning trees. There are several ways to find a bottleneck spanning tree. The key is to leverage techniques from MST algorithms. Here are the main approaches. 1. Minimum spanning tree algorithms, Kruskal's or Prim's. Since every MST is a BST, simply find the MST of the graph using either Kruskal's or Prim's algorithm. The resulting tree is guaranteed to be a bottleneck spanning tree as well. This is often the most efficient way. Kruskal's algorithm *. 1. Sort all the edges in the graph in non-decreasing order of their weights. 2. Initialize an empty spanning tree. 3. Iterate through the sorted edges. If adding an edge to the spanning tree does not create a cycle, add it. 4. The resulting spanning tree is the MST, and hence, the BST. Prim's algorithm *. 1. Start with an arbitrary vertex in the graph. 2. Grow the spanning tree one edge at a time. 3. In each step, select the edge with the minimum weight that connects a vertex already in the tree to a vertex not yet in the tree. 4. Repeat until all vertices are in the tree. 2. Binary search on edge weights, less common. This approach is less common because using Kruskal's or Prim's is generally more efficient. However, it illustrates the properties of BSTs. The algorithm is 1. Sort the unique edge weights in the graph. 2. Perform a binary search on the sorted list of edge weights. 3. For each edge weight W in the binary search. Create a subgraph containing only the edges with weights less than or equal to W. Check if the subgraph is connected. You can use depth first search, DFS, or breadth first search, BFS, for this. If the subgraph is connected, it means there exists a spanning tree with a maximum edge weight of at most W. Try a smaller W. Asterisk if the subgraph is not connected, it means there is no spanning tree with a maximum edge weight of at most W. Try a larger W. For the final edge weight W for which the subgraph is connected is the bottleneck weight. 5. Find a spanning tree of the subgraph containing all edges with weights less than or equal to the bottleneck weight. You can use Kruskal's or prims within the subgraph. Code example, Python with Kruskal's algorithm. This example will use Kruskal's algorithm to find the bottleneck spanning tree. We'll use the networks library for graph representation and union find data structure for efficient cycle detection. Explanation of the code asterisk. 1. Find _bottleneck spanning tree, graph, asterisk. Asterisk takes a network's graph as input. Asterisk edges equals sorted, graph.edges, data equals true, key equals lambda x, x2.get, weight, 1, sorts the edges of the graph in ascending order of their weights. Graph.edges, data equals true, returns a list of tuples like u, v, weight, w. The key equals lambda x, x2 weight part specifies that we want to sort based on the weight attribute in the edge data dictionary. The get, weight, 1, part handles cases where an edge might not have a weight assigned to it, it defaults to a weight of 1 in that case. Asterisk union find, number underscore vertices, initializes the union find data structure with a forest of nodes. The union find data structure is used to efficiently track connected components and detect cycles. Asterisk bst equals nx.graph, creates an empty networks graph to store the bottleneck spanning tree. Asterisk the code iterates through the sorted edges and uses the union find data structure to check if adding the edge to the spanning tree would create a cycle. If it doesn't, the edge is added to the spanning tree, and the connected components are merged using uf.union, u_id, v_id. Asterisk after adding an edge, it checks if the number of edges in the spanning tree is equal to the number of vertices minus 1, which is the number of edges in a spanning tree. If it is, the spanning tree is complete, and the loop breaks. Asterisk finally, it returns the resulting bottleneck spanning tree. If the graph is not connected, it returns none. To union find, from the union find library this class implements the union find, also known as disjoint set, data structure. It's used to efficiently track connected components in the graph. Here's a basic implementation, but installing the external union find library is recommended because it's likely more optimized. How the code works asterisk. The code implements Kruskal's algorithm, which is guaranteed to find a minimum spanning tree, MST. Since every MST is also a bottleneck spanning tree, the resulting tree is a BST. The algorithm sorts the edges by weight and iteratively adds edges to the spanning tree as long as adding an edge does not create a cycle. Cycle detection is done using the union find data structure. Key improvements and considerations asterisk. Asterisk use networks asterisk networks provides a convenient way to represent graphs and perform graph operations. Asterisk union find for cycle detection asterisk the union find data structure is essential for efficient cycle detection in Kruskal's algorithm. Asterisk edge weights asterisk the code assumes that edges have a weight attribute. You can modify the code to handle graphs where edge weights are stored differently. Asterisk connected graph asterisk the algorithm assumes that the input graph is connected. If the graph is not connected, the algorithm will not find a spanning tree. The code checks this and returns none if the graph is not connected. Asterisk efficiency asterisk Kruskal's algorithm with a good union find implementation has a time complexity of O, E log E, where E is the number of edges. Asterisk alternative MST algorithms asterisk you could easily adapt the code to use Prim's algorithm instead of Kruskal's. Summary asterisk. Bottleneck spanning trees are a valuable concept in graph theory and network design. They are particularly useful when you want to minimize the maximum edge weight in a spanning tree. You can find a bottleneck spanning tree by finding a minimum spanning tree, using Kruskal's or Prim's algorithm. The Python code example demonstrates how to find a bottleneck spanning tree using Kruskal's algorithm and the networks and union find libraries. Remember to install the union find library before running the code.